Hello everyone, today I am going to deliver a lecture on camber deflection and cable layout. The first part will be contained on cable deflection, which is including basic deflection formula, then math example of camber deflection, and then load deflection curve of prestressed beam. And second one is simple beam layout, which is contained on layout of pre-tension and post-tension beam. And third one cable profile, and it is contained on also location of the limiting zone for CGS and undesirable position for CGS zone limits. And math example of cable profile, which is determine the position of the CGS line. And third one we can see cantilever beam layout, and last one span depth ratio limitation. So let's start the camber deflection. So you can see here this is the reinforced beam, and this is the prestressed beam. So as we know, the reinforcement member or beam, initially when we applied the load on beam, then initially deflect, it will be deflect in upward, in downward. And if we imposed the external load, then it will be also go down in downward. On the other hand, we have seen in the prestress member or prestress beam, the initially when we have been apply the jacking force, then it will be act as upward. After we have imposing the external load, then it will goes the downward. Okay, so let's we can see the camber. So at first we can I'll just taking the all the reference from design of prestress concrete structure, third issue shown, it is written by T.Y. Lin. So let's see how the first some theory about the camber and deflection. Before cracking, the deflection of the prestressed concrete beam can be predicted with greater precision. That is a reinforced concrete beam, and under working load, the prestressed concrete beam do not crack, and reinforced ones do. Since the prestressed concrete is more or less homogeneous elastic body, which is obey the quite closely ordinate laws of flexural and shear, the deflection can be computed by the method of available and elementary strength of material. So let's see some of the basic deflection formula. So this is my hand note I have been writing here. For cantilever beam, so you can see that if the beam is imposed the point load, then the formula will be P L cube by 3 EI, and if the load is UTL, then P L to the power 4 divided by 8 EI. And if the variable load, then it will be the maximum deflection will be PL to the power 4 30 EI. For the simple supported beam, we can see the deflection will be if the point load, then PL cube by 48 EI. If the UDL load is applied, then it will be 5 PL to the power 4 3 divided by 384 EI. So another we can see for fixed support. So if we see the fixed support, then and the point load is applied, then the deflection will be PL cube divided by 192 EI. And the fixed support for UDL load, then we can use W L to the power 4 divided by EI. Okay, so let's see here the some deflection formula using this only this chapter. So you can see deflection prestress 5 W L cube divided by 384 EI, and for self weight 5 W self weight UDL for simple supported beam 5 W L to the power 384 EI, the same remain same as formula. For moment, so moment into L square 8EI. This is the new formula. And the for point load we have been seeing the PL cube by 48EI. Okay, so it is covered. So now uh, let's see another which is math example of uh, cable deflection. So let's see, this is an example. So at first we can write the question. So the question is a cantilever beam of 10 meter, simple support figure given below. This is the figure is given below. Is post tension with 785 millimeter square and a high tensile stitch to initial prestress of 965 MPa immediately after the prestress, and compute the initial deflection at the mid span due to prestress and the beam's own weight, which is modulus of elasticity 28 into 10 to the power 3 MPa, and estimate the deflection after 1.5 months. Assume the creep coefficient CC is 1.8 and the effective prestress of 285 MPa at that time. Okay, let's see, here is the beam which is 10 feet, and we can see the cross section is 300 into 45, and the top to the reinforcement length is 200 meter. Okay, so as we know the force into area into stress, we have been using this area into stress and founding this force. As we know the moment which is WL square by 8 for the simple supported. So moment, what is the moment? Moment is nothing but what is force into perpendicular distance. So after rearranging, then we have been found W, which is the UBL load, which is P8 PH, this is the 8 and it will be gone here, and 8 PH divided by L square, and found 9.03 Newton per millimeter. And modulus of elasticity is given here, and moment of inertia, as we know, P is 3 and D cube divided by 12, and found this below. As this information is given, now we can use the deflection of prestress 5 W L to the power 4 divided by 384 EI. So after calculating, we have been founding as this is the meter, and we've been converting it in a millimeter, as we've been seen on the other dimension is MPa or Newton per millimeter, and we've been found prestress is 18.4 millimeters. So remember, this deflection is upward. So as we have been seen in the previous here at firstly, this is the deflection of prestress in upward, so that's why it will be upward. Okay, so for due to self weight, we know how we'll calculate the self weight, volume into unit weight. How we know volume, as we know the 345 the cross section is given, and 1 meter is given, and 24 is unit weight of concrete, and found 3 to 4 Newton per millimeter. And the deflection is formula is here 5 W into L to the power 4 into 384 EI, and putting all this below, and found 6.6, which is downward due to self load. So remember, it will be downward. In the firstly, you have been found that due to prestress, it will be upward, and this will be downward. And now we have to calculate after the 1.5 month. So how it will be, we can see the cross section is given 45, and the 450 and 300, and distance between top to the center of the reinforcement, which is 200. So 200, as we've been the CG will be 45 divided by 2 is 225, and if we know here the CG is 225, if we know here the distance is 2, so distance between this and this, it will be eccentricity is 25. So you can see call distance between CGS and CGC. Okay, it will be important. So in the similarly, we have been we are finding the force, which is area into stress, which is given here, and eccentricity we have been found D divided by 2 is 220 divided by 2, and 200, and found 25. And in the moment, we know moment have been moment L to the power 4 into 8 EI, and moment means force into perpendicular distance, which is E eccentricity, and putting all this value, and found 3.7. These are also in downward. Okay, so after 1.5 month later, we have been found self weight is 6.6, which is upward. For free stress, we have been seen this 18, we have been found 18.4. These are the 18.4, and it will be taken 825 divided by 960, as the free stress is given here 825. That's why 825 divided by 965 and found 15.73. It is also upward, and self is gone downward, and it will also upward. And in moment, we have also taking the ratio between, and free stress is 825 divided by 965, and found 3.16, and it will also downward for in moment. So as we know, self-weight is positive, pre-stress is self-weight is negative, pre-stress is positive, and in moment is negative, and it will be multiplied with coefficient of CC. CC, this mean it is given the creep coefficient. Okay, and these are the answer we have been found. Ultimately 10.76 millimeter. It will be upward after 1.5 month. Okay, if there is another extra point load, then what will be happen? So let's see. If the another point load is arise, then we can use this formula, as we have been know the point load here. So that's why PL cube divided by 48 EI. This is the 48 EI, and founding 14.7 millimeter. And now we'll calculate the total, as we have been seen here, the total self-weight, pre-stress plus in. So it will be also minus point load. If we calculate the minus point load, then we will be found 4.08 in downward. Okay, so I think this also in depth. Now we can see the load deflection curve of pre-stress beam. Okay, so you can see here the load deflection curve of the pre-stress. In x-axis is deflection, y-axis is load, and this distance is we can compare to the pre-stress, and this distance we can the deflection due to girdle load, and this is the curtain, and this is the girdle load we have been seen, and linearly it will be in case which is wiring close and cracking load, and this is the ultimate load. If we go to the this book, we can see clearly. Okay, so here we can see load deflection curve. X is deflection, y is load, and this is the camber due to free stress, and it will be taken the minus, and the deflection due to girdle we have been founding here, and girdle load and uncertain load, and working load is here, cracking load is here, and ultimate load is here. So I think this also in depth. So now see the simple beam layout. So let's see the simple beam layout. Okay, simple beam layout. Okay, just giving time. Okay, so before going to the simple beam layout, we can see here some formula for computing mid-span camber due to pre-stress. For simple parabolic, we can see L square 5 by 8 into my 8EI. For offset parabola, the deflection will be L square divided by EI into M2 5 by 6 into M1. For straight CGS, L square divided by EI into M1. For 1 point harping, it will be L square ATI M2 plus 2 by 3 M1. For 2 point harping, it will be L square ATI M2 plus M1 minus M1 divided by M3 into 2L. It will be applied this formula. So these are the simple beam. What is the so let's read the theory first. The layout of the simple pre-stress concrete beam is controlled by two critical sections: the maximum moment and the in moment. These are the two critical. So maximum moment and in section. After this section are designed, the intermediate one can often by determine the inspection but should be separated separately investigated when necessary. The maximum moment section is controlled by true loading stage is initial stage at transfer with minimum moment is mg, which is girder moment acting on the beam, and the working load stage with the maximum design, which is mt. Okay, so let's see. Here is the layout of the pre-tension beam. We can see 1 and 2. After pre-tension it will be 2 and 3 and D, E, F and G. This type of pre-tension beam. So if we go to the another here, the layout of pre-tension beam, we have been seeing these are the pre-tension when the rebar is inserted, then it will be look like this. After the rebar inserted, the jacking force is applied, this beam will be acting this like it will be upward deflection, and after the jacking it will be also this like this, it will be upward deflection, it will be also upward, and this will be upward deflection. The prestressed reinforce is given here in we can see in downward, and in 1 point load. Another we can see there the 2 deflection is given here. So you can see layout the post tension. That means the after the casting it will be here. After the casting, jacking load will be applied. So after the casting, the girder jacking will be applied, and it will be act like this, and it will be also upward deflection. So another we can see another girder, it will be also upward deflection. Another we can see that the two cable profile, we can see one is sagging, another is straight. Another one we can see the is curved in upward, and another is straight. So we can see here layout of the pre-tension. Here is the layout of the post tension, as I have been seen here. This is the post tension. So we can see there the 6 picture of the cable profile layout. So let's see the it will be in depth. So let's see the third topic, which is cable profile. So at first we have been seeing the some theory. What is the cable profile? We can state the previous section that the layout simple beam is controlled by the maximum moment and in section. So these are the vital information, the maximum moment and the in section, so that the after 2 section can design and other section can determine by inspection. Okay, it seems happen, however, the intermediate point along with beam may be critical, and mainly instance would be desirable to determine the permissibility of the desirable profile for tendon. So to do this, the limitation zone of the location of the CGS first obtained, then tendon are arranged so that their centroidal will lie within the zone. So these are the cable profile theory, and then we can see the location of limiting zone of the CGS and undesirable position of CGS zone. Okay, let's see here. We can see here the limitation location of limiting zone of CGS, and the right side the undesirable profile for CGS zone limit. So at first we can see on the beam, the top is the point load, which is the beam elevation, and another we can see the girder moment and the total moment. So girder moment is deflection upward, and total moment also upward. And the upper here is the another limiting value. We can see here the KT is the top current, here is the KB is the bottom current. The distance from these two top current is here 1, and distance to this distance is here 2. So this is the upper limit we can see, and this is the lower limit. And the hash section we can see, we have to provide the scaffold this section. Okay, we'll see how can we define this, how can we find this zone. So undesirable position for CGS zone is limited. We can see here the upper limit too much near the bottom. So these are the upper layer, so too much near the bottom. Bottom means these are the bottom of the beam, and this is the lower which is cross the bottom. So that's why this will be not accept. So another one we can see upper limit too far away from bottom. So this is the upper limit. So this is the bottom of the beam. So this is the far away from bottom, and lower limit you can see this is that. That's why it will be not accept. Another one we can see this will be not accept. What is this? This is the we can see upper and lower limit crosses. So this is the upper limit, so it is cross suddenly, and this is the lower limit, it is cross in the suddenly. So that's why we cannot provide the reinforcement this zone. Rather we can focus this zone. We can provide this shaded area and the reinforcement for prestressed girder design. Okay, so I hope then these are the index. So now we can show the math example of probable profile, determine the position of the CGL. So let's see. At first we can read the question. Now we can see the preliminary design for 15-meter post-tension beam is given layout within tapered. Tapered, that means this is the tapered. Top flange and symmetrically I section as shown below. This is the shallow and 10 steel wire 9.mm diameter with the anchorage are used in pre-tension FRMC 985 MPa and FCE 786mm, 7XCA MPa. Reference is 35 MPa, and determine the position of the CGS line, livelihood, and superimpose that on the beam. Total is 6.5 Newton per millimeter. And in addition, the weight of the beam itself is girder mg, which is main girder, which is given 18 kilonewton per meter, and top, and the total we can see 265 kilonewton per millimeter at mid span. Okay, let's see. Here is all the dimension is given here. The depth is 850, and bottom we can see web 300. Here flange we can see 350 and web 100, and distance is 90 and 40 is given. This is the top current, this is the bottom current, and CGS is given, and 274 and 274 is also given here. So let's start. We can see the information is all the information is given here. Now we can calculate the force, which is the area into stress, and found in this below. After finding this below, the initial force will be area into initial force, which is found this below, and this is the how we will calculate this is the formula of what is the is the top current to the upper limit. Okay, so we can calculate top current to the upper limit, which is mt divided by f, and found this value from kt to the upper limit, and r2 is girder divided by f naught, and found this value. F2 is from bottom current to the lower limit. This is the bottom current. We can see this kb means bottom current to the lower limit. This is the distance is very important, and moment of inertia have been found, and area we also found. Now we can see radius of gyration r equal to root over I by a is found. CB, which is bottom, and is divided by 2, and found 425. And KT we know r square is divided by CB, and found 27. As this the symmetry, that's why top current and bottom current value will be remain same. So 274. So now after the founding here 274 from CG to this distance K top, this is the found 274, and K bottom 274 also as the same. And now we have also found A1. A1 means from top current to the upper limit. So you can see here A1 top current to the upper limit. So if we calculate here, this is the top current. Top current to the upper limit we have been known here upper limit. If we draw there, this is the upper limit. So this is A1, and same way A2 we have been found 1 and 2 6, which is the okay, bottom crown to the lower limit, this is the air to and found, and the distance between trees gap, how will calculate? We know the total here 274, and 274 is total top count to bottom count distance, and thus deduct the A1, which is 492 and 156. So we can see we have been found this shaded zone, which is upper zone and lower zone, and now what we will do? So after finding this value, then we can use the reinforcement or free stress rebar in this zone only. That's why we can find this value. Okay, so let's see, when tension is allowed, the tension, then we can see the region will be increased. How many region will be increased? We can just use this formula, just how just little bit will be region will be increased. Okay, so I hope that this math example also in that. So now see the cantilever beam layout. Okay, let's go. So we have been seen here, if we are already talking about the location CGS. You can see here the garter moment and total moment, beam elevation, and limiting zone, lower limit, upper limit and lower limit. And here's the undesirable position. Undesirable, that means we cannot use this profile. Okay, so we can see upper and lower limit cross. These are the upper limit, upper limit too much far away, upper limit too much away, upper limit too much near the bottom. That's why we can use this profile. Rather, we can use this location of the upper and lower limit. We can see this example also, how we can use this formula. Now you can see cantilever beam layout because of the balancing. Another we can see here the location of CGS by ultimate design, moment diagram for total working load. You can see here total working load, and moment diagram from ultimate load M into M total, and limit for CGS we can see here from. Okay, let's see here the another is cantilever beam layout. Here is a cantilever beam layout. At first we can read some theory that because of the balancing reduction moment, cantilever beam can be economically use the prestressed concrete structure, especially for certain favorable span and loading heavy beam. These basic theories and method for design cantilever beams are same those for simple beams, but work designed for more complicated because of the several factor must be carefully considered. These are the certain portion of the cantilever are subjected to both positive and negative movement depending on the position of the live load. And number two is obtain the more severe loading condition, partially loading and span must be sometimes be considered. And third is in cantilever the moments is produced, the load in certain portion are often counterable by load, counterbalance load by the position. Hence the moment are sensitively change the external load. Because of this, the sequence of the application superimposed load and beam must be carefully considered are executed. And number four, if the beam is precast, care must be exercised during erection and transportation of the beam. At all times of supporting condition, assume the design must be realized for beam and even the slight change of the position. And number four, cantilever beam are often more sensitive temperature change, which might cause the excessive deflection. And last one is the ultimate capacity. A beam may be relatively low, heavy, partially loading possibility, and the coexistence of high moment on shear at the certain critical section may also tend to reduce the ultimate strength in the cantilever. Okay, this was our some point. We can see here the typical layout of cantilevers. If the cantilever beam, then the cable profile will be like this. If long span, the short span will be like this. If the long span, then it will be like this. long anchor span. The anchor means these are the anchor. It will be like this, and a straight tendon. We can use also straight tendon. And we can see here the typical layout for double cantilever. If the cantilever is double, so it will be we can use cable this for short span. For tapered section cantilever, we can use this type of cable profile. And this is the straight tendon. For balance cantilever brace, we can see. For long cantilever, we can use this type of cable profile. The graphically method for CGS we can see here, the cantilever beam and dead load moment live load, and live load cantilever, and so many things. And we can see the here some lever arm couple total moment diagram and examples. So these are in depth. So last topic we have been seeing the last topic, the span depth ratio limitation. So let's see, these are the span depth limitation. The span means these are the span, of the beam or brace, and these are the depth limitation. For the region of economically and aesthetically higher span depth ratio are modest, always used for prestressed concrete. For reinforcement concrete, higher ratio are possibility because of the deflection can be much better control and prestressed design. On the other hand, when this region get too high and camber and deflection become quite sensitivity, the variation of loading is properties of materials in magnitude of the location, prestress and temperature. Furthermore, the effect of vibration become more pronounced. Okay. These are the end of the lecture. So if you have any question, then let me know. I hope that you can enjoy this lecture. If you have any question, then let me know. I hope you can. I am able to answer your question. So I am just giving the summary. The same at first. At first, I have been seeing the prestress some formula of deflection or for cantilever, simple support and fixed support, and then we can see the for prestress the deflection will be upward, and for RC deflection is lower for initially purposes. And we can use the deflection formula and calculating the prestress pretension member and compute the initial deflection and the deflection after 1.5 month. And we can see here for UDL, and we can also include the point load also, then we can see what will be happen. And then we can see the load deflection curve of prestress. This is the load deflection curve. And then we can see the layout of the pretension beam and layout of the post tension beam. These are the layout, the general layout. And then these are the important, which is called cable profile, the location of the limiting zone. These are the we will apply. And undesirable, that means we cannot use this profile. So this is shattered zone, we cannot use the steel, rather we can use this steel for upper and lower, steel between upper and lower limit. And we can see we can see an example of tapered section and finding the location of the shaded zone and current zone and air zone. And after we can also upper and lower limit. After finding this, we can also if we allow the tension, then it will be into something, then it will also we have been seen here also. Thank you everyone. If you have any question, let me know.